Okay, today's the 13th. Thank you.
Wait, Bruce, do you have my test?
Alex, the answer to that question is no. Oh, hold on. Are there more down here? Did you take it with everybody else, or did you take it in the test center?
I took it with everyone else.
You did? Oh, I see. It's Dylan's fault. Dylan's test is right at top of yours. Okay. Okay. Let's go through it. Given the vectors u and v, we had to do various things. Find unit vector in the direction of u. Unit vector in the direction of u is u divided by its magnitude. So 0, 3 divided by 3, the magnitude, which is 0, 1. 2, u dot v, dot product of the two. 0 times 4 plus 3 times 3 gives you 9, the dot product. Number 3, cosine of theta, dot product of the magnitudes. Dot product we just did is 9. The magnitude of u, we just said somewhere along the line, was 3. The magnitude of v is square root of 4 squared plus 3 squared. Square root of 25 is 5. So we end up with 3/5. Jesus, I hope. No, see, I didn't even simplify it. It's 9/15 here. I didn't even simplify it. Okay, which is kind of poor on my part, really, but there you go. Number 4, projection of u on v, dot product, magnitude of v squared times v, one way of doing it. Dot product is 9. The magnitude of v is 5 squared, 25 times v, 4, 3. Okay. So that answer 4 is D. The way I've got it is 9/25 v. Okay? Everybody okay here? All right. 5. Given those vectors, 0, 0, 3, 0, 4, 3, 1, 2, 0. Find various things. Cosine of the angle. Cosine of alpha, rather. Cosine of alpha is equal to, this is one of the direction cosines where we did this out. It's equal to u1 over the magnitude of u. That's equal to 0. If you think about it, u is 0, 0, 3. That's heading up the z-axis. The angle that makes with the x-axis is a 90-degree angle, the cosine of which is 0. Okay? Or you could actually use the fact that x-axis can be represented by the vector 1, 0, 0 and find the angle between the vector 0, 0, 3 and 1, 0, 0 by using dot product over the product of the magnitudes, and you'll still get 0. Okay, you get 0 no matter what you do there. Because that's the answer. A vector perpendicular to the parallelogram determined by these two is their cross product. And that's what we want to do then. We want to cross these guys. So let's do it. Where u is 0, 0, 3, v is 0, 4, 3. So, cross this out, cross this out. We're going to get 0 minus 12. Cross this out, we get 0 minus 0. And cross that out, we get 0 again. So their cross product is a negative 12, 0, 0, which you can do various. So you could take a negative 12 out and get 1, 0, 0. I don't know which way I did this. What did I do here? The 1, 0, 0 is what I had for the answer, okay? So this, everybody okay with that? All right, good, all right. Number 7. Area of the parallelogram determined by the vectors. The area of the parallelogram is equal to the magnitude of the cross. Well, we just did the cross. We found that to be a negative 12, 0, 0. The magnitude clearly is 12, okay? So that's 12. The height of the parallelogram, this is where you probably are better off going to number 9 and getting the volume, and then going back to number 8 to find the height. Omar.
Can you push that down?
Oh yeah, I can do this. There. Okay. So I'm going to go to number 9, which is the volume, which is the triple scalar product of W with a cross. Take the absolute value because there's no guarantee it's going to be positive. Depends on the order of things. So we want to take W, which is 1, 2, 0, dot that with our cross product to get a negative 12 plus 0, so that's 12. So the number 9, the volume is 12. The area of the parallelogram is 12. The volume is base times the height. Therefore, since the volume is 12 and the area of the base is 12, that leaves a height of 1. That's probably the easiest way to do it, is do it in that order. Okay, but you can do another way to find the height, of course, is to find the magnitude of the projection of W on the cross product, which isn't all that bad anyway, so either way. Any questions on any of those? Okay, fine. 10 through 14, you're given a bunch of points. 2, 0, 0, 0, 3, 0, 2, 2, 0, 2, 3, 0. A lot of zeros here. Okay. Well, they're all in the xy plane. It's kind of interesting. Find the equation of the line PQ. To find the equation of the line PQ, what we need is a direction vector PQ, okay, which would be negative 2, 3, 0. And we need a point. Well, we've got P and Q to use. I'm going to use point P. So the equation of the line is going to be 2 minus 2t for the x. The y is the 0 plus 3t. I mean plus, 3t. And the z is equal to a 0 and a 0t. So z is 0. Okay. Anybody else in on that? Okay. 11. The relationship of those lines, PQ, which we have here, and RS. So to find the relationship, we need to find RS. Okay. Well, right off the bat, let's do RS. Let's do the direction vector first for RS, which is 0, 1, 0. That's the direction vector. Just take the vector through R and S. Obviously, not a constant multiple of this direction vector. So, what do we know? It's not a constant multiple, so they're not the same line, and they're not parallel lines. Okay? And I'll tell you something else. At this point, given that they're all in the xy plane, every z coordinate is 0 here, they're in the same plane. Well, if they're not parallel, and they're not the same, but they're in the same plane, there's only one possibility left. They must intersect without doing anything else, okay? Just by using your brains. They can't be skew lines because skew lines are in different planes, okay? These are in the same plane. But if you miss that, if you don't realize that, what's the way to tell if they're intersecting? Well, you see where the x's and y's are the same, and you check to see if the z's are the same at the same time. So let's do it. Let's find line RS. line RS would be, here's a point, 2. We got the direction vector. Okay. X is equal to 2 plus 0s. Y is equal to 2 plus 1s, right here. And the z is equal to 0 plus 0s, 0. Okay? That's the equation of line RS. Okay? Check it out. What I'm doing is using point R with this direction vector. And now, what do you want to do? You want to see, okay, where are the x's the same? For what value of this parameter? T equals 0. At t equals 0, x's are the same. Okay. The y would be equal to 0. That makes s equal negative 2. That's not the way we did it. Let's do it the way we did it, although that way works. What did we do? We set the x's equal. We set the y's equal. We found the values that make the x's and y's equal, and we check to see if the z's are equal. Well, gee, guess what? The z's already are equal. So right there, you know they're intersecting without going through this. All right, but you could go through this. Solve for t. Oh, you already have t here. T would be equal to 0. Subtract the 2. Divide t is 0. When t is 0, s is negative 2. When t is 0 and s is negative 2, x's and y's are the same, but the z's are automatically the same. I don't know, there's 50 different ways to do it. They all come out to the same thing. They do intersect, okay? Any questions on this? You guys all right? Okay. Adrian, everything okay?
Yeah.
Okay. All right. All right. All right, number 12. Normal to the plane determined by the points P, Q, and R. Oh, jeez. All right, so let's do that. All right. Normal to the plane, P, Q, and R. All right, here we go. This is number 12. P, Q, R. All right, we already have PQ somewhere along the line. Well, it's easy enough to do. Here's PQ, negative 2, 3, 0. Okay, PR, 0, 2, 0. To find the vector perpendicular to those two, okay? Normal to those two lines, two vectors, do the cross. Okay? All right. Okay, PQ, negative 2, 3, 0. PR, 0, 2, 0. Cross product is equal to, cross this out, cross out, 0 is minus 0. Cross it out, cross it out. What the heck? Cross it out, cross it out. Oh, good. We get negative 4. Okay. That vector is normal to the plane determined by those three, 0, 0, and negative 4. But you know what? You could have figured it out without even doing that. Why? Because they each had that 0 and the z coordinate. That meant those two lines were in the xy plane. And what vector of those is normal to the xy plane? Well, it's C. It's the one that has 0, 0, negative 4. Down the z-axis, that's normal to the xy plane. Probably could have saved yourself some time, and some people probably did it that way, by looking at it and just using your brains. Although you could do it out this way too. Okay, then the equation of the plane PQR. Well, we've got a normal, okay? And we have points. So we got 0 times x minus 2 plus 0 times y minus 0. And then you have a negative 4 times z minus 0 equals 0. So z equals 0. And that's the equation of that plane, which you could have got just by looking at the fact that all 3 points lie in the xy plane, which is z equals 0. That's the equation of the xy plane. How are we doing? You guys all right? All right? Everybody's okay? It just seemed like something bad happened to you all just before this class. Or maybe something bad happened to you just after this class began, when I started talking, or something. I don't know what it is. All right, this one was nasty. Cosine of the angle of elevation of that plane and the xy plane. Well, that plane is the xy plane, okay? So the angle of elevation is going to be 0. But I wanted the cosine. What's the cosine of 0? 1. And the answer is 1. So, talk to me, Liam. So you had 0, right?
I had 0.
Yeah, a lot of people did. A lot of people had 0. I'm sorry. It turned out to be, and it's typical of some of my questions. I try to make them as simple as possible, but their very simplicity makes them devious, like, you know what I mean? That's not my intent, but it turns out that way. All right, 15 through 17. Given the surface, x squared plus y squared minus z squared is probably the one I did in class. I do that. That's another thing I do. All right. But anyhow, the xy trace, let z equal 0, and we've got a circle. Yz trace, let x equal 0, and we got a hyperbola. Wait, this is the apple core, right? Yeah. All right. Xz trace, let y equal 0, and you still got a hyperbola. You get the two hyperbolas and a circle in the middle. Okay. And given the point 1, 1, 1 and rectangular, okay, 1, 1, 1. Okay. All right, what do we need here? We need r, that's this guy. That's the square root of 2. We need rho, that's this distance here. Square root of 3. And we need theta, which is the inverse tangent of 1, which is pi over 4. Okay, any questions on that? Okay. Hey, that looks like my watch.
Go.
Is it? Oh, it's not though. My watch is now back to January 1st for some reason. I don't know how that happens. Yeah, Happy New Year. It's now Monday, January 1st. It has 1/12/11. I don't know. It's messed, in other words. What's that? Yeah. That's true. That's a good point. All right. You guys ready to start the next chapter? Let's do it. Start the next chapter here. Next chapter is on vector valued functions. What's that?
I'm gonna get one.
All right, here we go.
So it's like a watch.
Oh, the watch, yeah.
Yeah.
All right. What's that? 19.
On the,
Test?
yeah.
19 was rho, square root of 3.
Could you just like put it back up?
Oh. This, yeah, rho is that distance from here to here. It's a distance from the point 1, 1, 1 to the origin, which is square root of x squared plus y squared plus z squared.
I mixed up the
It's easy enough to do. Shoot. Okay. We okay? Tim, you okay? One more? Ed? All right. Next chapter. This is chapter 12?
12?
I think so. This is on vector valued functions. Okay, vector valued function. Vector valued function, let me give you an example. Vector valued function is given in two space. Say, let's actually do one here. Let's do t sine t. This would define a vector valued function in two space. What it is an infinite set of vectors, okay? And what you do is trace a path given by the endpoints of those vectors. For example, in this case, let's say you let let's start t at 0. T at 0 gives us the vector 0, 0. We start here with the 0 vector. If you go to t equals pi over 6, okay, pi over 6, we'll get pi over 6 and the sine of pi over 6, which is 1/2. We'll get this vector. Hey,
Yeah, it's coming.
good. You made it.
Yeah, that's good.
Good deal. Hold on, Teddy. Let's see. You're in here somewhere, guy. Oh no, I lost your test.
That's alright, I didn't need that one anyways.
Yeah, that's true. That's pretty simple.
I'll tell you right now, Teddy got an 85.
85 for Teddy?
Nah.
That would be insulting to him.
86?
Oh, I seriously did lose it. My gosh.
Does that mean you have to give me 100?
I think it does.
No, that's alright. They forget about it.
No, we can't do that.
We'll drop it back.
No.
That looks like
Oh, there you go. Oh, Dylan, it's Dylan's fault again. Again, Dylan covered up somebody else's test. It's all Dylan's fault.
Probably like trying to steal my answers.
No doubt. All right. Probably not the best thing to record. Dylan stole your answers, you know what I mean? But anyhow. So we get a vector at pi over 6. And then if you have t equals pi over 4, you get another vector, pi over 4, 1 over the square root of 2 over 2. You're going to get this vector. When t gets to be pi over 2, you're going to have pi over 2, sine of pi over 2, which is 1. And you'll get this vector. And then as you continue increasing t, the sign will now start decreasing, okay? The x will increase this way, the sign will now decrease, and you'll get this, and then you get this. At pi, we'll have this vector pi 0. So what happens is you trace a path given the endpoints of these vectors, and you're going to get this. I know, it's pretty cool. You get this, and you'll trace out a sine wave. Okay, that's what happens. Your first problem, first example on your next lab is this very vector valued function where you have Mathematica draw these arrows, these vectors, and you can see that the arrowheads, the heads of the arrow, trace that path. That's a vector valued function in 2 space. Yes?
So, whenever you start vector notation, it would be like t is pi over 6, sine of t is whatever sine of pi over 6 is. Why wouldn't it be that your vector tail is at pi over 6 and then goes to whatever sine t is?
Because that vector, here, let's do it. T equals pi over 6. When written this way, is in standard position starting at the origin. This is the x component, and that's the y component. Okay.
How would you write it starting somewhere else?
Yeah, if you wanted to start it somewhere else at 1010, say, suppose you want to start at 1010, okay? That vector pi over 6, 1/2, would be equal to the vector 10 plus pi over 6, and 1/2 plus 10, 10 plus a half, 10 and a half, like this. And that would start it this vector, hold on, this vector is not correct. If you want to start it somewhere else, you would say the vector, you'd give it a point P, would be the point 10, 10, and Q would be this point right here. Okay, so it would be the vector PQ, given this point and this point. This is not the correct vector, okay? Because that vector obviously has a length that's not equal to this vector. But the vector PQ, where P is 10, 10, and Q is 10 plus pi over 6 and 10 and a half, is the same as this vector here, whatever one it was. That's how you would do it. You'd have to specify the 2 points, though. That's the advantage of the component notation, is you're always assuming you're starting at 0, 0. So you only need these 2 components. If you want to start it somewhere else, you can do it, but you have to specify the 2 points. All righty. Now, in 3 space, what about vector valued function in 3 space, which we will do. If you have, let's take this one. This is the poster child for vector valued function in 3 space. We're going to do a couple of things with this. Find its arc length and do some various things. What would this describe, this vector valued function in 3 space? Well, if you start t at 0, you're going to end up with 1, 0, 0. That would be this vector right here. We would start here at the point 1, 0, 0. Now let's see what happens as you increase t. As you increase t, cosine t is going to decrease, okay? Sine will increase. Now forget the z component. Cosine t sine t, what does that describe? If you had that vector valued function in 2 space, cosine t sine t, what would that describe?
It's a circle.
A circle. That's exactly what it would be. It'd be a unit circle in the xy plane where x is equal to the cosine, the y is equal to the sine. Now what does the z component do here? As you increase the t, the z is going to increase. So yeah, that's exactly right. So what starts at that point, let's say this is the point 1, 0, 0 here. As you continue increasing t, it's going to be a circular path that's lifting off the xy plane because the z component is going to be increasing. What you end up with is, yeah, and the proper term for it is, what's the proper term for this? It's, what is it? Helix. Who said that? Anthony. Anthony knows things. You know that? Anthony knows stuff. It's what it would be as a helix. And if you had 2 of them, okay, and took the opposite and have it turn the other way, you'd get a double helix, and it'd be your DNA, okay? And then if you connected these with little branches, these bands here, you get GCAT. Adenylene, these little proteins that connect these strands. Yeah. You guys know this?
GCAT.
What is it? GCAT. GCAT. And there's words for each of those. I don't know what they are. All right? But anyhow, that's what you get. We're going to be doing stuff with this here. Now, the point, why even have these vector value functions anyways? It turns out there's certain advantages to considering a path of a particle as a vectors, okay, as opposed to just a point moving in that direction. We can do various things with these vectors. We can find tangent vectors. We can find normal vectors to the path, all right, by doing vector operations. We can find things like velocity and acceleration along the path, all right. We can do all kinds of stuff. If we have a path that's described as a vector valued function, okay, it's going to have a velocity vector, It's going to have an acceleration vector. Okay. It's also going to have a unit tangent vector. Okay. And it's going to have a unit normal vector. And what we're going to do is take this acceleration and project it along the normal vector and project it along the unit tangent vector to have the normal and tangential components of acceleration. Okay? And if you're going to design a track, okay, at Daytona, I don't know if I said this before, I think I did, but that's what you need. You need those tangential and normal components of acceleration, and you need some friction force. You need a bunch of stuff. The mathematics of those tracks is pretty substantial.
Let's go to Daytona.
What's that?
Let's go to Daytona. Let's do it.
We should do a field trip, shouldn't we? When it gets real cold out, that's the time to go. Yes?
What's that about the point where it's all originated from? Something over 1t?
Okay, you got t hat with a t. That's that's the unit tangent vector. We have a velocity vector, acceleration vector, and it's called the principal unit normal vector because this has two normal vectors, one in the other direction. There's only one principal unit normal vector that points inward in the direction of motion. We're going to do all these things. But right now, we can do this much. Let's say we're given r of t is equal to x of t, y of t. The velocity vector, okay, this velocity vector is going to be r prime of t. It's just what you would expect it to be. Okay? And the acceleration vector is going to be the derivative of the velocity vector, which would be the second derivative of our vector valued function. Okay? Like so. We can take derivatives of these things. We can integrate these vector valued functions. We're going to do that. And we can find the length of the vector valued function by taking the sum of the squares of the respective components. That's obvious. Find the magnitude. We can find limits of these vector valued functions. We can do all kinds of stuff. How do you find the limit of this vector valued function? You take the limit of each component. I think you're given, yeah, you're going to be given some of these to do. Right, find the limits. One in particular I know you're going to be given. I'm pretty sure anyways. All right, how are we doing so far? All right, we can stop there. Okay, that should be enough for the first section. Just defining the limit, the vector valued functions, doing some limit things. Then I think the derivatives and stuff come into the second section. Okay, so 12.1 is what you should be working on. And what we'll do tomorrow, we'll continue with this tomorrow. And we'll do those normals and tangential components, and we'll do them all in curvature, all kinds of cool stuff. Find the length of the vector valued function. We have math team today. Yes, pizza coming in. The pizza, though, they said they would get it here, again, as soon as they could. Evidently, there's a lot of department meetings. I have a department meeting, but, Kyle, how you doing?
It's Tuesday schedule, right?
Monday.
Today's Monday.
Wow.
Oh, man, I have notes. I have recordings. I have all kinds of stuff. Okay, all set? Math team, though. All right? Team.